Hello everyone. In this video, we are going to talk about the t-test. This is a very common test that is used in statistics, and we can use it in engineering as well in lots of different places. So here, as one of the videos under the playlist Engineering Mathematics, I want to talk about this test. So what is a t-test? The t-test is used for hypothesis testing, which we're going to talk about. And the goal of it is to determine whether there is a significant difference between the means or the averages of two groups. So you have data from group 1, you have data from group 2. You want to see if the averages of these two groups are quite a bit different, right? So for instance, you have class A and class B. They have the grades on the same subject, let's say, for instance, engineering mathematics, and you want to know whether on average the class A grades are quite a bit different than class B, like better, worse, or anything like that, okay? Now, this is specifically used when the sample sizes that you have are small, okay, like less than 30. So when the number of data in the sample is small, this is the good test to do. And also when the standard deviation of your population is unknown. Why is unknown? Because let's say, for instance, if I talk about the same example I mentioned, so if you want to know the standard deviation of grades on engineering mathematics, right? Then you need to go, for instance, let's say in the US, you have to go and find all the classes that are teaching this course all over the country, get all of those grades, and then find the standard deviation. And most of the time, you don't have access to such data. So most of the time, the standard deviation of the population is not known. So before we start talking about how to do it, the application of it, and so on, the major thing that we need to know all the time is what are the assumptions behind this test. First thing is the data should be continuous, okay? So we know in statistics and in probabilities, there are some distributions that are continuous, some of them are discrete. If you forgot about that, I have a video under the same playlist about different distributions, different PDFs. You can look at that, and here we assume that the distribution of the data in general is continuous and approximately normal distribution or Gaussian distribution. Now you might say in many cases in real life, the data are not normally distributed. I mean, these days, if you look at the grades in most of the classes, you see that the grades are not perfectly normally distributed. Most of them are like bimodal or something. And sometimes or many times you don't have a large number of data. So n is less than 30. Could you still use this test? Then the answer is you better not. If you don't have enough of data and your data is not normally distributed, then there are other tests we can use. One of them is called the Wilcoxon signed rank test, and the other one is called the Mann-Whitney U test. In future videos, I'm going to show you the Wilcoxon and the Mann-Whitney, okay? The W test and the U test. So I'm going to show you those in future videos. Now, if your data is not normal, but you have a bunch of data, you can still use the t-test to a good extent, to a good level of safety due to central limit theorem. If you don't know what central limit theorem is, I recommend you watch my video on the same playlist. I talked about the central limit theorem. Also, if you don't know how to determine whether a data is normally distributed or not, I have another video on the same playlist that talks about normality test. Okay, so I have videos on both of these topics to check whether data is normal and the central limit theorem. Okay, so that's the first assumption. Second one is the data that you get are randomly selected, okay? So you're not going to only pick the grades from your best students or your worst students to kind of show something intentionally. You have to get all of the data and randomly, and that is going to show the actual hypothesis test results. The other thing is the variance of these two populations or samples, the populations from which you pick the two samples, they should be equal. Okay. Now there is also one that has unequal variance. I'll show you that. And then if it's a pair t-test, which we're going to see, the data should definitely come from the same subjects, which we're going to see that as well. Now, where are the applications? It's in all sorts of topics. So in medical researches, for instance, if you apply a treatment and you want to see if the treatment was effective or not, or like it was just a placebo effect, you can do that. In education, if you did something and you want to know whether it improved the grades of the students or not, you can do that. In manufacturing, if you want to, for instance, perform a heat treatment or anything on the part and see whether it improved the strength of the part or not. Okay, in psychology, about, again, some behavioral experiment comparisons. So anytime you want to compare two groups, okay, whether they are two different groups or whether it's the same group before and after some kind of treatment, you can use the t-test. And that is the power of this method. So now let's talk about formulas and different types of t-tests. So there are three types of t-tests. The simplest one is called one sample t-test. So here you only have one group. You might say, oh, if you have one group, where's the other group? So here you compare the average of that group or sample to a known value. What is that known value? That is the average of the population. So this is a special case. This is where you know the average of the population, okay? And you want to compare the average of the sample to it, okay? So that's a very special case. For instance, let's say I know that, for instance, the average of the men height in US is about 6 feet. And now I go ahead and grab a sample of people, 20 people, somewhere in my class or somewhere from the boys, and I measure their height and I come up with, I don't know, maybe 5.9. So 5 feet and 9 inches. And then I want to know whether this class is on average shorter than the average of the population or it's not really significant. Okay, so this is the first type of t-test. Now, here you need to calculate two numbers. One of them is called degree of freedom, which in this case is the number of data in your sample minus 1. So n is the sample size. The other one is called t-statistics, which is calculated by the difference between your sample average and the population average, and divided by this kind of normalized sample standard deviation. So here the sample standard deviation is divided by the square root of the number of data in the sample. So you get this t-statistics value. You also need to get this degree of freedom. And then I'll show you, once you have these two numbers, how you can check whether your hypothesis testing is giving you that you accept or reject the null hypothesis. So you might say, what is null hypothesis? What is the other hypothesis? So here, let's talk a little bit about this hypothesis testing. So what is this? So here, you come up with a hypothesis. For instance, your null hypothesis in t-test, which we call it H0, is that there is no significant difference between the average of the sample and the population, or group 1 and group 2. Okay? In the one sample t-test, the hypothesis is that, well, between the sample and the population, on average, they are not really significantly different. They are almost the same thing. This is your null hypothesis. You assume they are the same. Alternative hypothesis, or H1, is no, they are not the same. Okay, so you assume that basically your mu and mu naught, or in this case x bar and mu naught, they are not the same thing. Okay, so here you assume that they are not the same thing. Let me change the mu to x bar here. So here is better. So we say the x bar and the mu naught are not the same. There is a significant difference between them. This is what we call a two-tailed test, Or, so as long as they are not equal to each other, as long as they are different, that is basically means X bar could be bigger than mu naught or could be less than mu naught, as long as they are not equal. Now, if we say, well, no, I assume that X bar is bigger than mu naught, or I assume that X bar is less than mu naught, so you only consider one of the two scenarios, that is called the one-tailed t-test. So one-tailed t-test is more specific than two-tailed t-test. Here I said the average of the height in this class is different from the average of the height in general population. Here I say no, the average of the height in this class is bigger. So my class is on average taller than the population. Here I say the average is less than, so my class on average is shorter than the average population. Okay? So if you just say they are not equal, two-tailed t-test. If you take one direction, then we call it one-tailed t-test. And the way that we check whether H naught is good or whether H1 is good, we accept or reject one of them, depends on whether we do a two-tailed t-test or we do a one-tailed t-test. And I'm going to show you that, the difference between them. So these are the two hypotheses that you have. Now you have to accept one or reject one. That is called the hypothesis testing. So how would you do the hypothesis testing? For this one sample t-test, the way that you do it is you go ahead and calculate the t statistics, which is exactly this guy here. So this t is the t of stat. You calculate this number because you have the data for it. You have X bar and S and N from the sample. Mu, you already know it. And then you need to go to what we call a t-table. And from that t-table, you find another t, which is called t-critical. So in that table, we have a critical value of t, and then you compare your statistical t with the critical t. If the absolute value of your statistics t is less than the critical from the table, you reject the null hypothesis, okay? If not, then you cannot reject it. Another way to say this hypothesis testing is there is another thing you can find from the t-table other than t-critical. There is another value you can find, is called p-value, which I'll show you what p-value is. If p-value is less than the significance level alpha, then you can reject the null hypothesis. So here I changed this to H naught because that's how I call the null hypothesis, not mu naught, H naught. Okay, so now the question is, what is the p-value, right? How do you find the t-critical? And what is the significance level or alpha? And I already also introduced to you this degree of freedom. So there are several things that I need to tell you what they are. So first, let's start with one of the most important ones, significance level or alpha. What is this? So significant level or alpha is a number between 0 to 1, which is the probability of rejecting the null hypothesis when it was actually true. So it's the chance of making an error. Okay, you should have accepted H naught. There was no difference between them, but you actually rejected it. What is the chance of you rejecting it, which is what we call a type 1 error. So type 1 error is when your null hypothesis is good, you reject it. So alpha is that. Of course, the smaller the alpha you pick, you are reducing the chance of making an error. And remember that in statistics and in testing, there is always a chance of making error. Okay, so for instance, the patient could not be sick, but you might say, well, the patient is sick. Okay, or the grades of the two classes are basically the same. You might say, well, I don't think they are the same. So there is always a chance of making error. There is type 1 error, type 2 error, and here we just focus on type 1. Type 2 is the opposite, okay? So we can talk about that separately. But here, alpha is the probability of a type 1 error. Now, as I said, the smaller the alpha, the better the chance of you not making a mistake. So what values of alpha are common? The most common value you typically pick is 5%. Okay, but if you want to be more conservative, you can go to 1%. And if you don't want to be conservative, you might go to 10%. So 90% you are right, here 95% you are right, here 99% you are right. Typically, most of the tests go with 95%, but again, many people will go with 99%, depending on how sensitive the result of the test should be. And if it's not super critical, you might use a basically bigger alpha. So typically, these two numbers are the most common ones. So that is alpha. And you have to pick a number yourself, the chance of allowing error. Degree of freedom, or DF, is what? Now, you learned that in this kind of test, DF is number of data minus 1. So what is degree of freedom in general? Degree of freedom is the number of independent values in your calculations that can vary. Okay? So the number of independent values that in your calculation can vary, that is what we call the degree of freedom. Now, you might ask, why is it that in this one sample t-test, the degree of freedom is the sample size minus 1? Where does that come from? Well, here, if you have n data points in the sample, so you have x1, x2, all the way to xn, right? You have n data points. Then, once you know the average, once you determine the average, since average is determined based on all the other numbers, if you fix that average and set that average, then basically among these n numbers, only n minus 1 of them can change, because some of these n numbers should be n times x bar, correct? So some of the numbers should be n times x bar. So if I pick x1, x2 all the way to xn minus 1, this xn is not freely, I cannot freely change xn. Why? Because some of these n numbers, as you can see, should be n times x bar. So once x bar is set, you only can change n minus 1 out of these n numbers to keep the same x bar. That's why your degrees of freedom is n minus 1. Okay, that's one thing. The other thing I want to briefly mention is this S here is called the sample standard deviation. This is different from the standard deviation for a population. So for a population, sigma, the standard deviation, is summation of the data minus the average squared divided by the number of data. For a sample, it is equal to the summation of the data minus their average squared, but divided by n minus 1, okay? And this is, by the way, it's not the standard deviation, it's the standard deviation squared, so it's called variance. If you want the standard deviation, you have to take a square root, so you have to do it like this, right? So that's one thing that you need to pay attention to. This is a sample standard deviation. This is a population standard deviation. And they are calculated differently, okay? Their denominators is different. Why do we subtract the 1 here? There is a big explanation on that, and that is removing bias and everything, which it needs a video of its own. So maybe in one of the future videos, I'll talk about why n and n minus 1 are used in populations and sample. In population, you have lots and lots of data. In sample, you only have a limited number of data. So if we subtract this 1, we can say that as n gets bigger and bigger, this S ultimately will approach the sigma. But if I use n in this formula, as n gets bigger and bigger, S will not approach sigma. S will have a difference with sigma, which we call bias. So to avoid that bias in sample, to avoid the bias between the average, the standard deviation of a sample as the sample size gets bigger, and the actual population standard deviation, here, mathematically, we can show that we need to subtract a 1. Okay, so just keep that in mind. So this is about degrees of freedom and significance level. Now, the last thing I need to talk about before show you the t-tables is p-value. What is p-value? Because here we said another way to reject the null hypothesis is to find p-value and compare it against alpha. So what is the p-value? Okay, so p-value is basically the probability of observing a test, a sample, a test of statistics on a sample that is as extreme as the one that you just calculated, assuming that the null hypothesis is true. So here, assume that the null hypothesis is true. So assume that the average height in this class is the same as the general population. What is the chance that you get a sample for which the average height is 5 foot and 9 inches as opposed to 6 or anything like that? What is the chance of observing another sample like that, okay, or in general? How much chance do you have? Okay, now, of course, when you have small p-values, that means the chance of observing a class with this height and saying that this height is the same as the 6 feet average of the population, the chance of observing such a thing is very rare. Most of the samples that I have seen, and I assume that they are the same as the 6 feet, they were like 5'11". They were like 5'11 and a half or something, right? Or 6'1" or anything like that. So the fact that you are 3 inches away from that, that is very rare for calling these two to be the same. So the smaller the p-value is, that is a bigger evidence against H0. So when p is very small, you should reject the null hypothesis. Hey, I don't think they are the same. It's very rare to see such a sample. But if it's a big p-value, yeah, 50% of the time I get classes with that kind of thing, then guess what? It's weak evidence against H0 and you can accept it, right? So here you accept it, here you reject it. Now you might say, what is small, what is large, huh? So that depends on the alpha. As you can see, we have to compare p against alpha. So let's say the alpha we picked is 5%. And the p that you get from your t-test is less than 1%. Clearly, this is way less than 5%. So here it's a strong evidence against it. So I'm going to reject the null hypothesis. On the other hand, if p is way more than 5%, 6, 7, 10, 12%, 20%, then I can accept it and say, hey, these two are not statistically different. But if it's between 1 to 5%, it's kind of moderate evidence. It's not really easy to basically accept or reject. Now, if we want to go based on this method, since p is less than alpha, we have to also reject this one. But here we do it, but we are not 100% sure as much as when we are way less than 1%. Okay, so here we reject it, but we are not as safe as this top case here. But if we want to accept or reject, we can do it basically by rejection. But again, it's not as strong. It's moderate evidence. Good. So now you might say, where do you get your t-critical, or where do you get your p-values? Where do you get these? As I said, they are coming from these t-tables, or basically t-values. So this is one sample that you can see here. Here is a t-table where you can directly read the t-critical. So what you need to have is alpha and the degree of freedom. So the columns here represent alpha and these guys represent degree of freedom. So let's say, for instance, let's do one example here so I can tell you exactly how it's done. So for this kind of one sample t-test, this is one kind of example. Let's say you have a machine that is supposed to fill bottles of soda. and it should put inside each one of them 500 milliliter of soda, right? You can apply it to a gas station or anything. Now, we filled 10 bottles with this machine, and we calculated the volume of soda in each one of them. We took the average of those 10 bottles, and we found that it is putting on average inside of them 492 milliliter, and the standard deviation of the sample is 8.6. And again, we have 10 samples. We want to know if this machine is underfilling, because you clearly see that this number is less than that 500 mil. So are these two different really? Okay, are these two different? So what you do is you form the t statistics by subtracting the x bar from what you expect to have from these machines. And in the denominator, you divide s by the square root of n. If you do that, your number is going to be negative 2.94. Now, you need to go to the t-table and use what? You need to use a degree of freedom, which in this case is n minus 1, n is 10, so you get 9. And we want to use a 5% chance of type 1 error. So with 0.05 and 9, we go to the table. Let's see what we get. So if we go with 9 and with 0.05, which is here, and here, if you look, the number is 1.833. And it's interesting here, I get a 2.262. And you might say, well, these two numbers are not the same. Where do you get this number from? Okay, here I have to tell you something. Remember on the top, we talked about the one-tail and the two-tail testing, correct? We said that whether they are equal or not, or whether what? One is bigger or less than. Here, if I want to do a two-tail t-test, or I want to do a one-tail t-test, the alpha that I'm going to use is going to be different. The alpha that you use for a two-tail versus one-tail, they are different alphas. Really? How? So this is the part that you need to know. If your test is a two-tail test, the alpha that you use is actually half of the alpha that you originally used. So if they give you a 5%, you actually use 2.5%, and you go to the table with that number. But if it's a one-tail test, you actually use that alpha itself. So in this case, if I want to do a two-tail test, I have to go with half of that, which is 0.025. So I have to go down this column. And if you look, this is the number that you get, 2.262. And that is this number that you see here. You see? So because I'm using a two-tail test, I use alpha over 2. And in this case, do we accept or reject? Because the absolute value of this T of critical here, if you compare these two, or if you compare them without the sign, you see that this is in the distribution to the left of this, so, or in magnitude, this is bigger in magnitude than that, you have to reject it. So the fact is, no, this machine is doing something different from the average machine. If the average machine is filling 500, this machine is doing something different. Now, to say machine is underfilling is basically not correct. Okay? So here I got this from some book, and this is not perfectly correct to say. Why? I cannot say machine is underfilling. I have to say machine is different, or statistically different from average machines. Okay? If I want to do underfilling, that means I have to assume that my H naught, instead of being X bar is equal to mu or not, here it should be different. It should be, hey, X bar is less than mu naught. If you do such a thing, now that means you are doing a one-tail t-test. Okay, if it's a one-tail t-test, as I just mentioned for you here, let's see. If it's a one-tail t-test, you have to actually use that 0.05. And how would you make sure that you do your hypothesis testing? So here it depends on, in one-tail t-test, is it a left-tail t-test or a right-tail t-test? What is left-tail? Left-tail means the population mean of sample is less than the mean of the given population. So basically means X bar is less than mu. This is called a left-tail t-test. If I assume X bar is bigger than mu, that is called a right-tail t-test. Okay? So what I'm doing here is a left-tail t-test. So I have to compare my t statistics against negative of t at, let's say, 0.05. And if you remember, t at 0.05 was this number, 1.833. So really, if I want to do a one-tail t-test, I have to compare this number against negative of what? 1.833. Which one is smaller? Clearly, this is smaller than that. So again, that means I should reject the H naught. And that means the answer is yes, it is really underfilling. Okay? So yes, it is underfilling because my T stat is less than negative of the T critical. Okay? Yeah? So you might say, well, your left t-test was X bar is less than mu and you rejected it. That means it's not less than mu. No. Actually, your null hypothesis is always that this thing is not correct. So it is like this. If you really want to be correct, your null hypothesis is that X bar is not less than mu. This is your H naught. And your H1 is, well, X bar is less than mu. So in this case, I have to reject H naught and kind of basically, it's not correct to say, but kind of accept H1, right? So I have to say, yes, the machine is underfilling. So H naught here means X bar is not less than mu. Here means X bar is not bigger than mu. And H1 is the exact opposite of that. So in this case, I have to reject H naught, accept H1, and say, well, yeah, this machine is kind of selling less than what it is. I don't know, maybe to save money for the owner, right? It doesn't give you 500, it only gives you 492. Some of the gas stations are like that, right? So you go and you want to fill in your car with 15 gallons, but if you take a sample, take some kind of measurement, and you see that it's not really selling you a gallon each time, it's just selling you maybe 0.95 of a gallon, okay? So basically stealing, that's what it is. So here is a one sample t-test and the difference between one tail, two tail, left tail, and right tail. Now, you might say, well, fine, you got this table and that was good. What about the p-value? So let me show you. So the p-value here is equal to the probability of the t that you find from the table being bigger than your t statistics, less than your t statistics, or bigger, 2 times bigger than p of t bigger than absolute value for two-tailed or left or right-tailed t-test. You might say, well, what does that mean? You made it even hard to understand. So let me show you what I mean by that. But Before I do that, let me first show you how to get the P number in MATLAB and how to perform a t-test in MATLAB. So in MATLAB, the command to use is called t-test. And you pass to it the entire data of the sample, x. So here you don't pass it the average, okay? It calculates x bar and s and n all from the sample data that you give it. And then you give it mu, and then alpha, you give it some significance level, alpha, right? If you don't, probably it uses 0.05. Mu is that known average of the population. And then for the tail, you say left, or you say right, or you say both. Okay, both means a two-tail t-test. Left and right, of course, left and right, one-tail t-test. And it returns two numbers for you. One is the p-value that I'm going to explain to you. The other one is h. This h, if it's 1, that means reject the null hypothesis. If it's 0, that means you cannot reject it. You don't have a strong evidence against it. Okay? So remember, at the end of the day, we accept or not reject the null hypothesis. So here, I'm going to go with this command in MATLAB, and I have to create data here for this test that the x of it gives you ultimately x bar of 492 and s of 8.6 and 10 data points. So while my mu is 500, the x, I need to, as I said, generate data from a normal distribution such that their average is 492, their sample standard deviation is 8.6, and I need 10 data points because I don't have those data. I just have the summary of the data. Okay, so here I artificially make those data in MATLAB. So you know, in MATLAB, the command randn generates data from a normal distribution. Now, if I say randn of n and 1, it gives me n data. But you know, their average is 0 and their standard deviation is 1. So to make their standard deviation s instead of 1, I multiply them by s. In this case, s is that 8.6. So now their standard deviation is going to be 8.6 instead of 1. And to shift their average from 0 to that 492, I add 492 to it. So now I will get 10 data points with that standard deviation and that average. So let's go ahead and generate. So let's say these are the data that I read from those bottles. Now, if I say what is mean of x, you see, it is not exactly giving me that. And you might say, why not? And if I go with the STD of x, that should also not be the number that I want. Okay, so you see, it did not work as perfectly as I wanted. And you might say, why not? Because if I generate this data with randn, these are just 10 random numbers. These rands are working great when you have a lot of numbers. Then in large numbers, their average and standard deviation gets close to what you want. But if it's only a few data, there is definitely no guarantee. So what I should do is first go ahead and get a rand of 10 and 1, 10 data points. Now look at the average of these numbers, okay? Rand n, sorry. If I go ahead with mean of z, look, you see, their average is not 0. And if I do STD of z, look, that's not 1. So first, I have to normalize this data, say z equals, basically, z minus mean of z, and then divide the whole thing by STD of z. So first normalize the data, force them to be average 0 and standard deviation of 1. Now these are different than the original data. Now if I perform on these guys again, you see their average is 0 and the standard deviation is 1. So now this data that I call z, this is good data. Now I can do the same transformation that I did, okay, and instead of this I used that here. So I performed that linear transformation from z to x. Now these x's, if you look at their average, they are 492. And if I look at their standard deviation, that is about 8.6. You see? So I'm going to use these data points along with that mu. And now I'm going to use that command that we just saw together, right? So this command here. And remember, I have a mu of 500. So now I give it x. X is good. Y is going to be mu in this case. Alpha is going to be 0.05. And I don't need here that part. I need tail to be both. And then I'll do also a left one for you. Look. Your h is 1. Remember, 1 means what? 1 means, and look at your p-value. Your p-value is 0.01. So look at your p. You see, it's less than 0.05. And h of 1 means what? Let's go back and look at it. H of 1 means you reject the null hypothesis. Yes, I have to reject that. These data, these bottle readings are clearly different from an average of 500. So I have to reject it, and here, because my p is less than the alpha, so I'm looking at this scenario here, I should reject it also. So it's moderate evidence. It's not strong, but it's barely bigger than 0.01, okay? You see, it's a little bit more than 0.01, but still less than 0.5, so I'm safe to do that. Now you might say, what if... First, let's look at this number. Where did they get this 0.0164, right? Where did they get this number from? So for a two-tailed t-test, the number was 0.0164, right? This is the p-value that I got. How do I get it from this p-table? So look here. Remember the t-stat that I had in this case. The t-stat was 294, okay? 294. So here, if I go and I look here, right? Look at my t's for degrees of freedom of 9. So what I want you to focus on is this row here. You see that for alpha of 0.02, that's 2.398. For alpha of 0.1, that is this one. For alpha of 0.005, that is this one, and so on and so forth. Now here, remember, it's a two-tailed t-test that I did. So I need to find where the t at that 9 degree of freedom, this t, passes the number that I had, which was 2.94. So where is it that I passed this number 2.94? So where is it? It's right here. It's between these two that I passed 2.94, between these two alpha values. It's somewhere between these two that I passed 2.94. It's between 2.8 and 3.2. Now, where is that? So here you can do an interpolation. You say, well, at 2.8, I'm at 0.01. At 3.25, I'm at 0.05. If my number is 2.94, what alpha, what probability? Because these probabilities, these are your alphas, okay? What number do I get? And in this case, the number that you will get is basically half of this. So it is going to be 0.00 and then 82. Okay, so it's a little bit closer to 0.1 than 0.05, and that's because 2.94 is closer to 2.82 than 3.25. So that is the number that you will get, and you multiply it by a 2, and guess what? You get this number. So first of all, you get this number by interpolation. And then you multiply by 2. And that is how you read the p-values, by interpolating from this table. Now, if it was a left-tailed t-test, let's go ahead and do a left-tailed t-test in MATLAB, see what p-value I get. So here, I make this left. I still reject it, but look at my number, 0.0082, this number that I just mentioned to you. Here, you directly read the number. That is going to be your p-value as opposed to multiplying it by 2. So you just read that, and that is exactly what I have. The number between these two, which was 0.0082. You see? So this is how you can read p-values once you have your t-stat and once you have your degree of freedom. On that row of degree of freedom, you find the two alpha values. Between their t-values, you have your t-stats. You do interpolation. You interpolate between the alphas. The alpha that you interpolate, that is going to be either your p-value or you multiply it by 2 if it's a two-tailed t-test. Okay, so this was a one sample t-test that I showed you. Now let's move on to the two other types of t-test. One of them is called two sample t-test. So here you do actually have two samples, and these two groups or two samples are independent from each other. So getting data from one is not going to affect the data from the other one. Okay, so we call them unpaired or independent t-test. Your null hypothesis is that the average of the data, the average population of these two samples, mu1 and mu2, are the same. So these data are coming from two similar or two identical populations on average. Alternative says no, they are different. So here, how would you calculate your t-stat? Your t-stat is coming from the average between the difference between the two samples, the sample means. And in the denominator, you have what we call a pooled standard deviation, SP, a pooled standard deviation. And then it's multiplied by a square root of 1 over n1 plus 1 over n2, where these n's are the number of data in each sample. And the pooled standard deviation is n minus 1 times s1 squared plus n minus 2 s2 squared divided by n1 plus n2 minus 2. And this is your basically the degree of freedom that you have in this case. So this guy here is your degree of freedom. And the reason again is you have total of n1 plus n2 data, but since the averages are fixed, two of those data are basically fixed. You cannot change them because some of the data in each group divided by the number should be equal to the averages. So your degree of freedom is n1 plus n2 minus 2. And this is your t-stat. And again, from t-stat and your basically t-critical that you find from the table, you can do your hypothesis testing. This is assuming that the variance of the two populations that these two samples are coming from are equal. So they are coming from basically two populations that have equal variance. If you don't know that the standard deviation of the two populations these two samples are taken from are equal or not, you can go with unequal variance. This time we call the t-test Welch t-test. Here your t-stat is, if you look at it, your t-stat is a little bit different. This is going to be your t-stat. And the degree of freedom, the approximate formula for it is this big of a guy. So with this degree of freedom and alpha, you go and find your t-critical. This is your t-stat and you compare. And again, here with that degree of freedom and alpha, you calculate your t-critical and again, you compare. Okay, so if you know or you don't know that they are equal variance or not, then the formulas that you have for t-stat and the degree of freedom are going to be different. Now in MATLAB, if you want to do it, the command to use is called t-test2. So here you have to use 2 for it. So it knows it's two separate samples, and then you give sample X and sample Y data, and then you can give it an alpha value, and then the other thing you have is you can tell it whether they are equal or unequal. Okay, so that is another thing that you can give it. Okay, let me get rid of this. Seems like it should be pasted here actually. So here you have to say the var type, the variance type, are they equal or are they unequal? So you can say equal or you can say what? Unequal, okay? And that is how you do a two-sample t-test. Okay, so this is what we have here. Now let's look at an example here. So let's say here I have done a tensile test on two sets of specimen from 3D printing plastics, and I bought these plastics from two different vendors. Okay, so here you can see the average and the standard deviation for the yield strength of these two groups in megapascal, and I want to know if the yield strength of these two plastics from these two different vendors are significantly different or not. I assume equal variance and I use alpha of 0.05 in here. Okay, so group A, they have 8 data points. Their average is 102. Their standard deviation is 4. Group B, I have 10 specimen. I have 98 on average, and I have 3.5. Again, you see here, I don't have the original data A and B, but when I use this command here, when I use this command that I just showed you, here I need to make sure that I have the data in X and Y. So before I use that command, I need to go and basically generate the data here for group A and B artificially, and then force it to be with those averages and standard deviations. So let's go ahead and use the same technique that we did. So first, I go ahead and look at my z values. Remember, my z values were 10 data points, and if you remember, their average and standard deviations were good. So since there are 10 data in the z, correct, I can use that for my second group, for group B. So I can go ahead and directly use this and multiply by 3.5 and then add the 98. So here I can go back and use this one here and say this is X of B, right? And as you just saw, I multiply by a 3.5 and add 98. So let's go ahead and do that. So this is X of B. These are my data in specimen B. For A, I need to regenerate some Z data again. But this time I'm going to generate 8 data points like this. Then force them to be perfectly normally distributed. I can always check it. You see they are good. And now I use the transformation and generate A data. And for A, I need to use 4 and 102. So 102 and 4. Okay, there we go. So these are the data generated in group A specimens. These are the data generated in group B. And now I want to know whether the data average of the data in group A and B are the same or not. So I use my test. So this is going to be X of A versus X of B. And I assume that they are equal variance and my alpha value is 0.05. Yeah. And you see H is again 1. That means I should reject it. They are not basically equal. There is some significant difference between them. But my P is actually not really strong. It's about 0.037 or 38. So it's getting close to 0.05. So it's moderate, basically evidence against it. But still, since it's less than 0.05, I should reject it. Now, you might say, what would happen if you just make this and say, hey, I don't know if they are from two equal groups or not, so their variance could be unequal. What happens then? And you see you still reject it, but this time your P is even closer to 0.05. So even it's a little bit weaker than last time is. Okay? Yeah? So if it is from equal or unequal variance, the result might be a little bit different. And if this P was a little bit bigger, like more than 0.05, guess what? You had to reject it. So in this case, you clearly can see that you had to reject it. And you can also get your T value if you want from the table, right? So in this case, your sample pool is 3.73. Your T stat, based on the formula we had up there, is going to be 2.26. Your degree of freedom is going to be how much? As we learned, it is n1 plus n2 minus 2 for equal variance. So 10 plus 8 minus 2, that's 16. And if we go with that 16 and with alpha of 0.05, you will get a 2.12 from the table, but your T-stat is bigger than that, 2.26. So of course you have to reject it. You see, so clearly you can see whether you do it here or whether you do it in MATLAB, both of them will reject the null hypothesis. So the last part that we need to look at is called paired t-test or dependent t-test. Here you have two groups of data, but they belong to the same subject. You have two samples, you have two sets of data, but not from two separate subjects. They are from the same subject. They are what we call pre and post data. So you did some kind of treatment, some kind of operation, something on the same group, but before you do it, you collected some data, some performance, something, and then after that treatment or operation, you recollected the same performance data. So it's before and after, or we call them pre and post data. And you want to know whether that treatment had any effect or not. So again, it's the same subject. That is the important thing. The T-stat that this time calculate is very simple. It's the average of the differences between the pre and post data. So here, this you calculate the data between group X post, let's say, and group X pre. You subtract this data and get this vector D. And then the average of that D is D bar that you do. The standard deviation of that is going to be SD, and then you divide it by the number of pairs because it's the same group. So if the pre-data has n data, post-data has also n data. So you divide it by square root of n. That is your T-stat. Your alpha is given to you. Your degree of freedom is, of course, n minus 1, again, because you have n data. And the average is set. So with that df and with the alpha, you find some T critical, and you compare it against this T-stat, and that is the number you're going to get. In MATLAB, if you want to do it, the command is again t-test. So the same command is used for pair t-test and for the one sample t-test. But this time, you have to give it the pre-data and the post-data. You give it some alpha value and you give it a tail. Whether this tail is right or left or both or what, okay? And that is gonna give you back your H and P. So as the last example here, let's say in my dynamics class, to improve my students' grade, I introduced a new pedagogical methodology, and the grades of 6 students in that class that I had, these are their pre and post grades out of 100. I want to know whether this methodology that I used in the class was effective if I use 5% alpha. So the first thing you do, you start subtracting them. So you get the D vector, and here you basically get one of these data and then minus these before ones, right? So 75 minus 70, that's 5. 74 minus 68 is 6. This one is 6, right? This one is 5. This one is 2. And this one is 4. So these data here. Their average is 4.67. Their standard deviation is 1.63. And of course, you have 6 data points. So from there, you calculate your t-stat. Your t-stat is going to be 7002 with degree of freedom, which is 6 minus 1, 5, and with alpha of 0.05. You go to the table and you find 2571. And this is way bigger than that. So of course you reject it and you can say the program was effective. Or in this case, to better say it, is there was a significant difference between the pre and post data. Now, if you want to say that it was effective, it means it improved the grades, you have to say that the average of the post data is bigger than the average of the pre data. That should be your null hypothesis, and clearly this is a right tail t-test as opposed to a two-tailed. So here I have done that right tail for you in MATLAB. These are the data for group A and B, and I did a right tail with 0.05, and look here, your H becomes 0 and your P is almost 1. And H of 0 means you cannot reject the null hypothesis. So here basically I have to accept it and I have to say yes, this methodology actually improved the grades. From this group to this group, there is an improve. Okay? So that was the right tail t-test. So hopefully with all of this, you learned basically what kind of t-test to use, whether it's one sample, pair t-test, two sample, what are the degrees of freedom for each, and how to calculate t-statistics for each, how to read the t-value and p-value for different kind of tests, one-tailed, two-tailed, left or right, what alpha and what p-value to use, and whether to accept or reject the null hypothesis. And you can see some of the applications in engineering, in pedagogy, in basically quality checking and quality assurance, and so on and so forth. So thank you so much for your attention. I'll see you in the next video.